Hi, this is Involved Innovation YouTube channel. Welcome to the Kubernetes series. This is a beginner-friendly series where we will start from the basics and master Kubernetes. In this video, we will see about Kubernetes introduction and architecture. This video is very important to understand the Kubernetes. The topic covered in the video are, we will start with the introduction and then we will cover a brief history and we will see why we really need Kubernetes and what are its major functionalities and how Kubernetes works, what is control plane and explaining its components such as API Server, etcd or cluster store, controller manager, cloud controller manager and Kube Scheduler. What is worker node and explaining its components such as Kubelet, kube-proxy and container runtime. Now we will see about Kubernetes introduction. Traditionally, the applications are monolithic, that is, all the functionalities are bundled as a single executable which share the same code base. So we use the complete physical or virtual machine to deploy the monolithic service. With the advent of microservices, the monolithic applications are split into multiple smaller components based on its functionality. This facilitated us to individually scale, but interestingly, each microservice does not require full compute capability of a machine, which has resulted in the popularity of container. Huge credit goes to the Docker for playing a very vital role here. A container is a lightweight, standalone executable package of software that includes everything needed to run an application: code, runtime, system tools, libraries, and settings, etc. Containers are isolated from one another and from the host system, ensuring that the application runs uniformly regardless of the environment. So this made developer life even more happy because whatever you are going to develop in your local system, it is equivalent to whatever you are going to deploy to the production system. I have a complete video series on Docker, you can find that in my channel. With containers, I can scale the applications selectively, each unit running their own container. Now we have lots of containers. This creates a special problem: how to manage if some of the containers fail, how to manage these containers, how to scale the applications dynamically, if there is a sudden burst of traffic, how to increase the number of containers. This resulted in lot of scripts to perform this. Often this resulted in slow adoption of container technology because traditional enterprises are not willing to experiment containers in the production environment. This is where Kubernetes came into the rescue. Kubernetes is an orchestration tool. Orchestration in the real world meaning is the art and craft of arranging the musical composition by ensuring that the combination of different instruments produces a cohesive and balanced sound, where no single instrument overwhelms the other unless intended for performance. Here, the instruments are analogous to the container and Kubernetes does the orchestration. Kubernetes, why this name? Kubernetes is the Greek word meaning helmsman, the person who steers the ship. This is why the Kubernetes logo contains the wheel which is used by the helmsman to steer. Kubernetes shortened to K8S. Here the 8 represents the 8 characters between K and S. Now we'll see about a brief history of Kubernetes. Google started off Borg as an internal project for internal cluster management. Following Borg, Google introduced the Omega cluster management system, a flexible, scalable scheduler for large compute clusters. Using lessons learned and best practices from Borg and Omega, Google created Kubernetes. In 2014, they open sourced it and handed it over to the Cloud Native Computing Foundation, CNCF. From there, Kubernetes got huge adoption rate among different enterprises. Kubernetes and Docker. Docker builds application to image with Docker file. Then Docker file runs this image in container, whereas Kubernetes orchestrates these containers. So Docker is used to create the image and run it in the container, whereas the Kubernetes is used to manage these containers. Kubernetes performs tasks such as deploying the application, scaling up, scaling down as per the needs. So here the individual containers can be scaled up and scaled down, and we can able to define the state of each and every application. Let's take you have 1000 applications and each application has very number of containers and you have different number of containers as per the load. Then Kubernetes can able to handle everything. And Kubernetes also monitors the health of the container and brings up the unhealthy containers and abstracts the underlying infrastructure, service discovery, etc. We will see the major functionality now in detail. Abstracts underlying infrastructure. Assume you are managing the containers through the script. Then you need to deploy these containers on each infrastructure. It can be virtual machine or a physical server or a cloud server. Here, let's take each container takes 25% of computing power and memory of the underlying infrastructure. So after deploying 4 containers, then you need to manage the container in a new server. What if suddenly one server goes down? Now think you have hundreds of containers running. This is where Kubernetes shines. Kubernetes abstracts the underlying infrastructure. It helps in deploying the containers without worrying about the underlying infrastructure, and we can add new nodes or servers seamlessly. Kubernetes also finds the best node or instance to run a specific task. This information provided through a YAML file. It checks if the instance has all the criteria met to run the task. Next is self-healing. Let's take we have a food application, and for the food app, we have 3 microservices. We need to have 4 instances for recipe app, 1 instance of container for items app, and 2 instances of user app to withstand the incoming load. If we define this in the Kubernetes, Kubernetes monitors the health of each and every instance or the containers here. If any of the instance goes down or not responding, then the Kubernetes automatically brings up this new instance and manages the desired state count for each services. And one of the very important thing here is the Kubernetes is cloud agnostic. In today's world, enterprise solutions are heavily relying on the cloud provider to run the compute power required for the applications. Kubernetes abstracts the cloud provider since we will be using the Kubernetes API to manage the infrastructure in this cloud provider. So we can use multiple cloud provider, or moving from one cloud provider to another provider will be easy with Kubernetes. Now we will see about one of the very important topic, that is how Kubernetes really works. The Kubernetes works on top of nodes or instance. These are Linux nodes that can be physical server or any cloud service like AWS, GCP or virtual machine, or it can even be a ARM architecture machine like Raspberry Pi. Let's take we have 6 node, which is a cluster where Kubernetes is running, and it manages the containers. If any one node fails, how Kubernetes manages this cluster, where the information about this node in the clusters are stored, and how the containers in one node are moved to another node. This is where the Kubernetes control plane comes in, and also previously known as master node or head node. The control plane is another group of nodes. Its primary duty is to manage the cluster. The control plane can be a single or more nodes. Usually more nodes and odd count of nodes need to be used as control plane to ensure high availability and fault tolerance. The control plane is another node that has special Kubernetes components installed. The control plane monitors and manages the nodes in the cluster. The control plane contains API Server, etcd or the cluster store, Kube Scheduler, Controller Manager, and Cloud Controller Manager as their components. It is not recommended to run user applications on the control plane node. Use the control plane only to manage the cluster. The application runs on the worker node. So the worker nodes are the node where the real applications are running. Let's take here in this diagram, you have 5 worker nodes and 3 control nodes. Now we will see about the control nodes components in detail. First we will see about the API server. Communication between all the components must go through the API server. It exposes a RESTful API, a deployment YAML file, which is used to define and manage a deployment object, which ensures that a specific number of pod replicas are running at any given time. Deployment provides declarative updates to application, allowing it to roll out changes in the controlled manner, roll back to previous versions, and scale the number of replica as needed. We will learn more about deployment YAML when we get into hands-on. This deployment YAML is posted to the RESTful API exposed by the API server. The API servers performs the validation, persisting to the store, and changes the schedules to the worker nodes through Kubelet. Next we will see about the etcd or cluster store. The cluster store is a centralized data store based on etcd, which is a distributed key value data store. In the Kubernetes, cluster store is the only stateful part of the control plane. The cluster store holds all the persisted data needed to manage the state of the Kubernetes cluster, including information about nodes, pods, services, configuration, and more. It is a single source of truth for the cluster. A default installation of Kubernetes installs a replica of the cluster store on every control plane and automatically configures high availability. It uses a raft consensus algorithm to maintain consistency across multiple nodes. etcd prefers consistency over availability. This will hold updates to the cluster in order to maintain consistency. During this period, the application will work fine. It won't be able to update the cluster config. Next, we will see about the controller manager. Controller manager runs various controllers to manage the state of the cluster. Each controller is responsible for ensuring that the desired state of the particular resource matches the actual state in the cluster. The controller manager is essentially the brain behind many of the operations that keep the Kubernetes cluster running smoothly. Now we will see about the different controllers in the control manager. Node controller. Node controller is responsible for monitoring the health of the nodes and taking actions when node goes down, and also manages the life cycle of the nodes, including node addition and removal. Replication controller. The replication controller ensures a specified number of pod replicas are running at any given time and creates a new pod or deletes excess pods to maintain the desired number of replicas. Next is the deployment controller. The deployment controller manages deployment objects by ensuring the correct number of replicas are running and handles rolling updates and rollbacks of applications. Endpoint controller. Endpoint controller manages the endpoint objects, which tracks the IP address and ports of the pods, ensures that service endpoints are updated as pods are added or removed. Service controller. The service controller provides a stable endpoint for a set of pods. It abstracts the underlying pod instances, allowing clients to interact with the service without needing to know the details of the individual pods. The service controller performs service discovery and load balancing. Daemon set controller. The daemon set controller ensures that a copy of pod runs on all or some of the nodes in the cluster. It is used for deploying system level or node specific tasks such as monitoring agents, logging daemons, or networking plugins. Daemon set controller also manages rolling updates of the pods across all nodes, ensuring that the update is rolled out safely without interrupting the cluster's operation. Next and the final controller is job controller, which manages job objects to ensure that a specific number of pod completion occurs, handles the execution and termination of jobs. For example, you can create a job to process a large dataset. If you need to process a large dataset, this job is configured to run 5 pods in parallel, each processing a chunk of data. The job controller ensures that each pod runs to completion and retries any pod that fails. Once all 5 pods complete successfully, then the job is marked as finished. Now we will see about the loop in the controller. Each controller follows a control loop pattern, which includes watch. First, it watches the state of the cluster for changes. Example, new pod request, node failure, and then evaluate the current state of the cluster against the desired state. The desired state is the one which is given by the user through the pod spec YAML file. And then act takes action to bring the current state closer to the desired state. That is, if it finds some of the pods for applications are not running, then it can able to restart those pods and terminating unhealthy nodes and then bringing back the nodes. The key functions of the controller manager are state reconciliation. The primary function of the controller manager is to ensure that the actual state of the cluster matches the desired state specified by the user through the YAML file. If there is a discrepancy, the controller takes corrective actions to reconcile the two states. And then resource management. Controllers manage resources like pods, nodes, replicas, endpoints, and more. These are all key topics which we will be covering later in the series. And the next component in the control plane is Kube Scheduler. The scheduler watches the API server for the new work tasks and assigns them to the appropriate healthy worker node. We will learn about the pod later, where we will learn about the worker node. For now, understand pod is the execution environment to run one or more container present in the worker node. Kubernetes allows customization and extension of scheduling behavior through custom scheduler or scheduler extender. Key functions of the scheduler are pod placement. The primary function of the scheduler is to assign a new or unscheduled pods to nodes. This involves selecting the most appropriate node based on the various constraints and requirements. Next is resource allocation. Ensures that the resource requests such as CPU, memory of the pods are met by the available resources on the nodes, and avoids overcommitting resources on any single node to prevent performance degradation. And then the third function is policy enforcement. Enforces scheduling policies and constraints defined by users such as node selectors, taints and tolerance, and affinity and anti-affinity rules. We will learn about these different jargons later in this series. The scheduler follows a well-defined process to place pods to the node. First is filtering. The scheduler filters out the nodes that do not meet the pod's requirements. Common filters include checking node taints, tolerance, node selectors, resource requests, and constraints like pod affinity, anti-affinity. And then scoring. The scheduler scores the remaining nodes based on various criteria to find the most suitable one. Scoring functions may consider factors like resource availability, node utilization, balancing the distribution of pods across the cluster. There are various factors influencing node decisions such as resource requirements, node constraints, affinity and anti-affinity, node resources, and pod disruption budgets. And finally, binding. Once the best node is selected, the scheduler binds the pod to the node by updating the API server with the decision. The scheduler writes the binding information to the cluster store etcd via the API server. And finally, we will see about Cloud Controller Manager. This Cloud Controller Manager is very specific to manage cloud-based Kubernetes. The Cloud Controller Manager handles cloud-specific operations separately from the core Kubernetes control plane, which includes components like the API Server, Controller Manager, Scheduler. By decoupling the cloud-specific logic, the Kubernetes ensures that the core components remain cloud agnostic and can run on any infrastructure, whether it is on-premise or in a public cloud or in a hybrid setup. The Cloud Controller Manager typically includes the following controllers. Node controller, which is responsible for checking the status of the nodes, that is, virtual machines in the cloud environment. The route controller manages network routes in the cloud to ensure the Kubernetes pods can communicate with each other. Service controller manages the creation and maintenance of cloud load balancers for Kubernetes services. And then persistent volume controller, which integrates with the cloud provider to provision and manage persistent storage volumes. Now we will see about the worker node. Till now we have learned about control plane and various components in the control plane. The control plane is the one which manages the worker node. The worker node is the place where the application really runs. Now we will see about worker node and its components in detail. Worker node is a fundamental component responsible for running the application workloads. These workloads are encapsulated within pods, which are smallest deployable units in the Kubernetes. Each worker node is the machine, either physical server or a virtual machine. Each worker node has components such as Kubelet, kube-proxy, container runtime. Now we will see about each of these components in detail. The Kubelet is one of the very important component in worker node. The functions of Kubelet are receiving the pod definition, that is pod spec, from the Kubernetes API server, which is present in the control plane. The pod spec is the YAML file which defines the pod and the container that it should run inside it. Next, it performs start, stop and terminate. Kubelet interacts with the container runtime like Docker, Containerd or CRI-O to create and manage containers. It also ensures that containers are started, stopped and removed as per the pod specification. Here in this example, it creates 3 identical parts in the node running the nginx and exposes port 80. Monitoring. The kubelet also performs health checks on the node and parts running on it, and also monitors the resource usage, CPU, memory of containers of its nodes, and reports this information to the control plane. If the kubelet detects that a pod or its containers has failed, it follows the restart policy defined in the pod, usually always for deployments, and restarts the container. Networking. Kubelet ensures that containers are properly networked according to Kubernetes network policies, allowing them to communicate with each other and with external services. Volume mounting. Kubelet handles the mounting and unmounting of storage volumes that are attached to the pods, ensuring data persistence where required. Pod security. Kubelet also enforces security policies on pods, including network policies and pod security policies. It also manages service accounts and secrets, ensuring they are securely distributed to the container. If a kubelet can't execute a task assigned by the API server, then it reports back to the control plane, and the control plane decides the action to perform. Control plane can use the scheduler to find the next worker node which can execute this task. So the kubelet is only responsible for the worker node which it manages. It is not responsible for any other nodes in the cluster. Container runtime. The kubelet needs a container runtime to perform the container related task. The container runtime environment pulls the image and performs starting or stopping of the container. Before 2020, Kubernetes had native support for Docker. That is, Docker does not implement the container runtime interface defined by Kubernetes. In the past, there were not as many good options for container runtimes, and Kubernetes implemented the Docker shim, an additional layer to serve as an interface between the Kubernetes and Docker. From Kubernetes version 1.23, this special layer, Docker shim, is removed from the Kubernetes. Since December 2020, Kubernetes uses containerd directly as the container runtime, meaning Docker shim is no longer needed in the middleman role. I have a separate video on Docker internal architecture. You can find that video on my channel. Kubernetes supports container runtime such as containerd, CRI-O, and other implementations of Kubernetes container runtime interface (CRI). Next, we'll see about Kube proxy. Kube proxy is the network proxy that runs on each node in the cluster, which is responsible for local cluster networking. Kubernetes uses the operating system packet filtering layer if there is one and it's available. Otherwise, Kube proxy forwards the traffic itself. Kube proxy ensures that applications deployed in Kubernetes can reliably communicate with one another, regardless of the dynamic nature of the containerized environments, whether through IP tables, IPv6, IPvS, or other methods. Kube proxy plays a pivotal role in maintaining network connectivity and performance in a Kubernetes cluster. Thanks for watching. In the next video, we will get the hands-on and we will start with pods. So if you find this video helpful, share it with your friends. Thanks for watching.